Let's start, Professor Yang.
Okay. Thank you, everyone. Thank you for joining us. This is a special program organized by Photon Research, and the name of the program is Photon Spotlight. It was created to highlight exciting papers that was published in Photon Research. So Photon Research is a partner journal that was co-published by Chinese Laser Press and Optica Publishing Group. According to what we have found, the impact factor for the journal in 2022 is 7.2. That's a good sign to show the journal is running well and has been recognized by the community. And the journal is sponsored by and supported by not only just the readers and authors from the community and the people working behind the scene. In addition to myself, we have two deputy editors who have been sharing the load to take care of papers submitted to Photon Research. And from the table, you can see the position of Photon Research compared to many other top journals. Photonic research is doing pretty well, I would say. If you look at the number of papers published, you'll find actually it publishes hundreds of papers every year that allow us to accept papers that cover all aspects of research in the field of optics and photonics. And also, this is a good example to show that the papers that was published in Photon Research can get sufficient visibilities. And you can also see that various kind of topics can be accepted in Photon Research, from the cutting edge silicon photonics to conventional field of imaging, for example. And also in the various kind of way for Photon Research to highlight the paper that was published in the journal. So, for example, on the cover is a way to promote an author's work. And currently, when you submit a paper, there's an option to upload cover imaging. So I would strongly recommend authors to design nice pictures that is attractive to and simple to explain the science covered in your paper. And we most of the time we will choose the papers that that submitted the cover letter as example, cover imaging as example. And this is just an example showing the images that actually was designed by the author themselves. So sometimes I call, the engineer and researchers, not just engineer or scientist or physicist, they are also artists from what you've seen here. And also I want to emphasize, as a partner journal, we do have some advantages. For example, the papers that was published in Photon Research can be highlighted and promoted by different kind of platform in multiple languages, English and Chinese, all around the world. And in addition to that, as I said, we have very strong editorial board, and our editors have been proactively promoting the journals when they attend different conference. And in addition to that, you can see, in addition to this personal promotion, benefiting from the WeChat platform created by Chinese Laser Press, we can also have different ways to promote the research. And I can say, for example, based on the numbers shown here, the lot of fans are subscribed to the Chinese Laser Press WeChat platform. So that being said, there's different channels to promote our work. Here is an example of articles released from the WeChat platform. You can see there's some of article is about the interview actually we did with pioneering research in the field of photonics. And some of the article is about papers published in the journal. And some of those actually is about activities such as workshop organized by Photon Research. And all of those have attract a lot of attention from general public. And in addition to that, we do have things in mind to promote not only research, but also the people serving us. For example, in addition to associate editor, we also have assistant editors. Those are the young people just started their own independent research program. And we recruit them to help the review process. And in addition to that, sometimes for some paper we try to promote, we ask them to write some comments to highlight the innovation and impact of those papers. And in addition, all those ways to promote work, and we also have a way to recognize our appreciation for authors. For example, every year we chose 2 papers as Editor-in-Chief Choice Award. So in addition to this, as a recognition honor, each group will get a 10,000 renminbi. The money, of course, doesn't mean the value of the work, but it is a way, a kind of token for us to show the appreciation for the authors who consider photon research as a venue to publish a work. And I can tell you the secret to get this award. So it's not just judged by the impact factor citation numbers. Instead, it's about the innovation impact of the research. So sometimes we chose paper from a small group, and sometimes from a big group. And also the work can be theoretical work or experimental work. So there's no specific rules about what kind of work and what nature of the work should be selected. It's all about impact and innovation to the community. So in addition to all those, we also care about engagement. So in addition to papers, right? Because currently there's so many ways to share our opinion, promote the community. So that is why the motivation we created this what we call photon research webinar, which is about the conversation with a pioneering researcher in the field of photonics and optics. So the first one was launched in 2021. It was interview with Professor Marlon Scully, who did a lot of pioneering research in the field of quantum optics. And it was well received by the community. Then for the next one, the interview with John Bauer, we decided to change the form of the interview. So instead of letting me to interview the senior researcher, instead we asked them to work with the star student who has decided to stay in academia. For example, the webinar with Professor John Bauer. He was interviewed by his student Lin Chang. Currently, he is a professor now. So it also again was well received. So continue this way to promote the great researcher, because the conversation between the professor, the well-established professor, and the students surely give the audience a way to see the dynamics between the mentor and the students, and maybe help them to understand the way in academia to communicate and interact with mentors. Well, it's actually a very fun conversation. For example, the most recent one is an interview between Professor Connie Chang and Professor Hausen, and I would like to encourage you to watch the video. It's really fun and include a lot of interesting tips that will be helpful, especially for young researchers. So, in addition to all those, as I said, in addition to webinar and WeChat post, we also organize offline activities such as workshop once a year, and each year we carefully chose a topic that has found a lot of interest in the community. And you can see every year the topic is different. For example, 2021, when deep learning is emerging, and we organize this special workshop. And in 2022 is integrated photonics. And last year is about optical metasurface. In addition to workshop, we also have feature issue about this topic. Multiple ways to promote exciting topic to the community. And in addition to that, last year we have some special activities to celebrate the 10th anniversary of the journal. And I really want to thank the school who helped us to organize all those activities. The first one was organized in Tsinghua University. The second one was in USTC. And the third one is in Sun Yat-sen University. So in those activities, in addition to talks, we also organize panels. Probably you can look for online article, which include the transcript of this forum, this discussion. It's actually very interesting to read. So in addition to those, we also have feature issue. On looking back, in general, we publish 2 feature issue per year to promote the topic that is of interest to the community. And there are multiple ways to promote, to organize the feature issue. Sometimes it's initiated by the editorial board, but sometimes we do solicit input from the community. If you have something in mind that you wanted to promote your topic, I would like to encourage you to reach out to us. This email, you can send an email to, and I would love to hear more from you. And with that, I'll stop, and I wanted to introduce tonight's speaker, Professor Guoan Zheng, about the exciting topic published in the journal. It was selected as Spotlight on Optics in last December. So every month, one article was selected as Spotlight. And the reason this article was chosen is because of innovation and the impact. So have you heard of this ptychography? Probably some of them are not familiar with this topic. That is why you are here tonight. He will explain various kind of imaging system that based on the coded ptychography, and he will help you to understand and decipher what is the meaning of that. And so let's welcome Professor Guoan Zheng. So Guoan,
yes,
stage is yours.
Yeah, thank you. So let me share my screen. Can you see my screen?
Yes.
Okay, great. Thank you, Professor Yang Lan. In fact, I first heard your name and your work on microcavity when I was a student at Caltech. And at that time, my roommate was a member in Wahala's group. And it's great to get reconnected here. And also, it's my great pleasure to discuss some of the research projects in my lab. So in today's talk, I want to talk about this technology called coated ptychography, and I want to talk about its applications in both lensless microscope and endoscope platforms. So this is the outline. So first, I want to talk about the background, the concept, and the imaging model of this technology. And then I want to talk about different implementations, including how to hack a Blu-ray drive to build a device, and other how to build other few portable platforms. And I will talk about the label-free imaging with this intrinsic polarimetric contrast. And then I want to talk about how to combine this device with a flow cytometer to develop this opto-fluidic ptychography on a chip. After that, I want to talk about some extensions of this technology. The first one is that we try to consider the temporal correlation to improve the temporal resolution to perform real-time imaging of the object. And then I want to talk about how to perform this depth multiplex imaging. So we try to image the entire biological stack sample together using a car mirror. And finally, I want to talk about how to extend this approach to other imaging modalities, including how to implement this in the Fourier ptychographic microscopy and other applications like synthetic aperture ptychographic endoscope. So with this outline, so I will start from the background, the concept, and the imaging model of this technology. So if the audience is new to this field, so I guess the first question you might ask is, what is ptychography? So P here is silent, so just like psychology. So it pronounced like ptychography. The word, this tycho means to fold or convolution in English, and graphy means to write. So the take-home message here is that convolution is a main aspect of this technology. And the concept was proposed about like 50 years ago in this paper, and it's written in German. But I need to know that the modern form of this technology is a little bit different from the original concept it proposed. I want to start with this so-called short-time Fourier transform to connect the ptychography with this well-known signal processing trick. So let's consider we have a one-dimensional signal. So this is just a 1D signal. And you can do a Fourier transform so that you can get a one-dimensional spectrum output from this 1D signal input. So that is the conventional Fourier transform. The short-time Fourier transform is a little bit different. The key message here is that we will multiply this signal with this window function. So you can see this narrow window function here. So basically, we will multiply the signal with this narrow window function, and then we can get the resulting signal. And we then do this the Fourier transform to get the spectrum output. So this is the Fourier FFT output number 1, fast Fourier transform output number 1. So the next step is we are going to translate this window function. So you see that the original window function is here. And now we are going to translate this window function to the second position. We multiply this window function with the original signal, and then we get the product. And then we do the second Fourier transform to get the second Fourier spectrum. And we are going to move this window function. We're going to translate this window function to the third position, multiply with the original signal, get the product, and then we do the Fourier transform to get the spectrum, the third spectrum. So if we have this one-dimensional signal, at the end of the day, we can get this 2D spectrogram output. So the concept is very simple. So we just put the first spectrum at the first column of this 2D output, and then we put the second spectrum signal at the second column of this spectrogram output, and so on and so forth, so that we can get this two-dimensional spectrogram of this one-dimensional signal. So this short-time Fourier transform actually is related to the concept of ptychography. So with this in mind, let's take a look at the experimental setup of this conventional ptychography. So you can see here, so we are going to use a laser to illuminate this confined aperture. So this confined aperture generates a window function, just like the narrow window function I talked about in the previous slides. So that window function will multiply with the object, and the product will propagate to the image sensor by Fourier transform. And we are going to use this regular two-dimensional image sensor to capture the intensity of this spectrum data. So this is the typical spectrum data we capture by using this setup. And then we are going to recover the original high-resolution image of the object. Two take-home messages. The first one is we are going to use a window function to multiply with the object. So here we use this confined aperture to generate the window function. Second message is we need to translate this object to different positions. For each position, we will capture one spectrum data. So that is the two main take-home messages of this the regular ptychography approach. So let's take a look at the image model here. It's pretty easy to understand. So we have the object O. We are going to translate this object O to different xi, yi position. And at each xi, yi position, we will multiply this object with the window function. We call this a pop. Pop means the illumination pop beam. And after we do this multiplication, we are going to do the Fourier transform. And then we are going to take the absolute value, do the square. So that will be the intensity measurement we have. So this is the image model of this ptychography approach. And based on the captured spectrum data I, we are going to recover the high resolution image of the object O. However, there are some limitations for this conventional ptychography. The first one is that the resolution and the imaging throughput is very low compared to the regular light microscope. And this is the main reason why this approach is little known to biomedical researchers. And the reason is that, this conventional setup here, I show here, cannot compete with the conventional light microscope. Another limitation here is that this window function I described here is often unknown. And the reason is that this window function is related to like where you put the sample. If you put the sample closer to the aperture, you might have one window function. If you put the sample like a little bit far away from the aperture, you might have another window function. And it is also difficult to pre-characterize or pre-measure this function because like it's really related to how you position your sample. And that's why oftentimes we need to recover both the object and this window function at the same time. And it's a challenging problem. It's also called a bind recovery. And lastly, you can see that we capture the data in the Fourier domain. So that's why you see this spectrum data here. And most of the signal, most of the energy concentrated at the center of this image. And you need to use a high dynamic range detector to record the signal. And it is challenging to record the signal at the edge of this image sensor. So with this, the limitation in mind, so I want to talk about our solution, and our solution is called coated ptychography. With our solution, we aim to address all of these limitations, and we try to compete with the conventional light microscope. And we show that we can get a much higher imaging throughput, and we can get a comparable high resolution as the conventional light microscope. So I will talk about our solution, and I want to talk about like how to make this device, and then I will talk about the imaging model of this technology. So let's talk about how to make the device, and it's straightforward and it's also very interesting to do. So this is my finger. So I got a needle from the CVS store. So this is for blood sugar testing. So I'm going to use the needle to poke my finger so that I can get a drop of blood. And then I'm going to smear this drop of blood on top of this regular image sensor. This is how we smear the blood on the image sensor. And with that, we can get this, I call this a coated sensor. So we have a layer of blood cells on top of this image sensor. And it is called coated sensor. And with this coated sensor, we can then do this coated ptychography. The next step is we got this low-cost manual stage, and then we try to modify this manual stage with this stepper motor so that we can build this programmable stage. So this was done by several undergraduate students in our department. So this is the final prototype device. So we have the light source. It's a laser diode coming from top, the laser beam coming from the top. We illuminate the samples. The sample here is the microscope slice, and certainly you can put any sample you want there. And then we have the blood coated sensor pasted under the sample. I have a video to demo the operations of this platform, and I hope you can see the motion of this blood coated sensor under the sample. So you can see a slight motion of that coated sensor under this pathology slice. And during this process, we are going to acquire multiple diffraction images of the object. This is the pathology slice, and with those data, we can recover the high resolution image of the object. So this is the typical image we capture. So this is the diffraction pattern of a resolution target. And with this, the image we capture, and then we can recover the high resolution image of this resolution target. We can resolve like 300 nanometer line width on group 10 element 5 in this experiment. So this is another example. So the sample here is an unstained thyroid smear, So this is the clinical sample without staining. So this will be the raw image, and then we can recover the face image of the sample, and we can do face unwrapping. And also we can compare our results with the conventional microscope platform with this 0.5 numerical aperture objective lens. So with that, so let's talk about the imaging model of this coated ptychography approach. So this is the imaging model of the conventional microscope platform. So it's straightforward. Like we have two lenses. The first one is the objective lens, and then we have the tube lens. So in this regular microscope platform, so basically we use these two lenses to do two Fourier transform. So we have the object, we do the first Fourier transform, and then we do the second Fourier transform. And at the Fourier space, we have a pupil aperture there to perform low-pass filtering. So this is the imaging model. We will do the first Fourier transform of the object with the objective lens. And then we're going to apply, so we got this spectrum in the Fourier domain. And then we are going to multiply this spectrum with the pupil function of the objective lens. So we multiply this spectrum with the pupil, and we do the second Fourier transform. And then we can get the intensity value of the object. Typically, we don't do any reconstruction. The image you capture is a representation of the object itself. So this is the conventional microscope platform. So now let's take a look at this coated ptychography platform. So we have the object here, and then we have the coated sensor. Again, I smear a drop of blood on top of the image sensor to create this coated surface. So the image model is also easy to understand. So we illuminate the object with the pink wave, and then the light wave will propagate to the pink of this coated surface. So that's why we have the object here. We propagate this object propagate this object by a distance d1. So we propagate the object for distance d1 to the coated surface. And then we get this wave field called W. The next step is we are going to multiply this wave field W with the coated surface. So the coated surface here is the layer of blood cells. So we just multiply the profile of this blood cells with the object wave field. And then we are going to propagate the product for a distance of d2 from the coated surface to the pixel array. And there we are going to capture the intensity values of this light wave. So that is our diffraction measurement, I. And in the reconstruction process, we are going to do the phase retrieval from the diffraction pattern I we capture. We are going to do this alternating projection to recover the object light wave W. And from there, we can propagate this wave back to any position we want to recover the high-resolution object. So this is the imaging model of this coated ptychography platform. And the take-home message here is that compared to the conventional microscope, we replace two physical lens with two phase-space propagation operation. So in conventional platform, you have two lenses, and here we have two phase-space propagation. And then we replace the pupil aperture by this coated surface. So that is the basic idea or the take-home message. Actually, I have a question for our audience. So I hope like everyone can think about this question. So the question is, which types of blood is best for this coated ptychography technology? So in the experiment I showed you, I use my blood. So that is the human blood. We can also try different types of blood, right? We can try the fish, goat, duck, and chicken. So my question is like, which types of the blood is the best for this coated sensor, and why? I will stop 5 seconds here. maybe the audience can think about this question. Okay, so it turns out that the answer is the gold bud. And the reason is that the gold bud cells is the smallest among all animals. So this is the results by using this gold bud to perform this ptychographic imaging. So this is the captured raw image. So this is the recover high resolution image of the resolution target. And this is the recover image of the gold bud cells. So I smear this gold bud on top of the image sensor, and we can recover the phase and intensity of this layer. We also test like with other types of bud. Like for example, this is the result of fish bud. And you can see that the resolution is a little bit lower. And you can also see that the size of the fish bud is much larger than the gold bud. So the size of the gold bud is about 2 micron. And as a reference, for human bud, it typically is about 6 to 8 micron. And for fish bud, it's typically about 10 micron or larger. Okay, so the answer is the gold bud. And another question I have for our audience is that, can any crab make a good coated surface? So this we found this like at the farm on campus. We found this crab. If you zoom in one of these crab, and my student takes some of this crab, and he put this on top of the image sensor, and then he smear a small portion of this crab on this image sensor, and then we build the coated sensor and perform the experiment. So this is the result he got. So this is the recover intensity and the phase image of the coated surface. So this is the layer of the crab across the image sensor. We recover both the intensity and the phase image of that crab. And with this coated sensor, we can also recover the image of the object. And you can see here the image quality is not good here. And in terms of the resolution, you don't see the details of group 10. In terms of the background, it's not uniform. And the reason here is that you can see the coated layer here is not uniform, right? You can see there's some empty region. And also, you can see many phase web of this coated layer, this crab. The reason is that it's too thick in terms of the surface. So you cannot model the image as the product between the object and the surface. And again, the surface is too thick. So the take-home message here is that to make a good coated surface, we need to make a thin, uniform layer to modulate the light wave. We develop a process to make this coated surface. So we start with cover gas, and then we try to etch this micron level phase scatter on the cover gas. And follow after the etching of the cover gas, we are going to print this intensity absorber on top of this phase scatter, so that we can create an coated surface with both phase and intensity scatters. So this is the picture to show you like how to print those carbon nanoparticles on top of this etched cover gas. So this is the image sensor, and then we attach this coated surface on top of the image sensor. So with this device, we build a parallel imaging platform. So we put a coated sensor here, and we can image A samples at once. So this is the prototype device. So this is the recover image by using this lensless imaging platform. So this is the recover image of the resolution target using the green light. This is the recover image using the blue light. And we can also show you the corresponding diffraction pattern we capture. And you can see that the pixel size here is about 2 micron. And from the reconstruction, we can resolve 300 nanometer line width from this resolution target. So this is a video to show you the operation of this platform. So we continue to move this sample and capture the data. And suddenly we switch to a next field of view to repeat this process. So by using this parallel imaging platform, we can get about 0.8 numerical aperture. And this is the height is the numerical aperture for lensless imaging. We can resolve a 300 nanometer line width on the resolution target. Typically, we acquire 200 to 400 images in this process, and it took about 10 seconds to do that. And the effective imaging field of view is about 240 millimeter square, and we acquired the data in 15 seconds. So this is the sample reconstruction of phase target. So not only the intensity resolution target, we can also recover the phase information of the object. You can see that with the recover phase, we can calculate the height map of the sample, I mean the height map is like in a good agreement with the ground truth. We also try to image different types of object. Like here, we try to image a transparent optical prism, so we can see those phase ramp, linear phase ramp of that optical prism. So this is the recover phase image of a lens. And lastly, this is the recover phase image of an object. And I would ask our audience to think about what is the object. And it turns out that the object is bacterial colonies on the agar plate. So you can see the background phase wrap at the background. They are they are from the agar plate. So the agar is not even, not fat. So that's why you can see those phase wrap. And then we have this phase wrap from the bacterial colony. Another advantage here is that we don't need to do any focusing when we try to capture the data. So after we recover the light wave at the coated surface layer, so this is the recover light wave at the coated surface layer, we can propagate this light wave back to any position we want. So we can do focusing or refocusing after the data has been acquired. So after we recover this light wave at the coated surface plane, we can propagate this back to the correct position to get the high resolution intensity and the phase image of the object. So this is the post-measurement focus map we generated for different samples. So this is the recover high-resolution intensity image by using this lensless imaging platform. And we also compare our reconstruction with the image captured using this 40x objective lens. We can also show the difference here. So you can see that the difference is very small, and we can get a very good quality from the recover image. So this video to show you the field of view and the details we can get by using this lensless imaging platform. Different from the conventional light microscope, now the imaging field of view is no longer limited by the optics. It's just limited by how large is your image sensor. And here we can capture the entire pathology slice with high resolution and a large field of view at the same time. And we can zoom into different parts of this sample, and we can see the we can see the details of the cells on this pathology slide. We can also perform blood cell differential counting. So this is the recover phase image of a blood smear sample. So this is the recover phase of the white blood cells, and this is the recover intensity of these 4 different white blood cells. We also compare the reconstruction with the conventional optical microscope. So this is just a collection of different white blood cells we recover using this lensless imaging platform. And with this image, we can then perform differential white blood cell counting. So this is the important clinical procedures to test the health of the patient. Recently, we also try to use this platform to compete with the conventional interferometer measurement. So application here is for optical metrology. So this is the optical elements, free-form optical elements manufactured by one of my colleagues, Professor Ron Liang from the University of Arizona. So we capture the phase image by using our lensless imaging platform. And also we compare our results with the conventional cycle interferometer measurement. And you can see that they are in a good agreement with each other. So with that, I want to talk about different implementations of this platform. The first one is that we can modify a Blu-ray drive. So this is the Blu-ray drive you can buy online. And then we can take a part of this Blu-ray drive, and you can see that within the Blu-ray drive, we have the red laser, we have the blue laser. We can use this laser diode as the coherent laser source. So this is how we drive the laser. Also, we have the rotational motor, we have the translational motor. So with that, we can build this platform. So we illuminate the sample using the blue laser. And we use this motor to rotate the sample on top of this coated sensor. And then we capture the data. And with those measurements, we can then recover the high-resolution image of the object. So this is the recover image of the resolution target using this Blu-ray platform. So this is the raw image. You can see the resolution improvements here. So this is the raw image of the phase target. So this is the recover phase, and this is the high map of the recover of this phase target. So this is the raw image of the individual bacterial cells. So we can recover the high resolution intensity and the phase image of the bacterial cells. My student also do UV analysis by using this platform. So we got some UV sample, and we try to look for the materials within this UV sample. And we find a lot of different types of crystals in the UV sample. So these are 3 different types of crystals. So this is the additional crystals and the different types of cells, red blood cell, white blood cells, and some other stuff that we don't know. So something like that. So we don't know what is that. My question to our online audience is that which crystals is related to kidney disease? I stop here for maybe 3 seconds. 2, 1. It turns out that this calcium oxalate, this crystal is related to the kidney disease. So if you can find a lot of this type of crystals in your urine sample, then you have a chance to get the kidney stone. So this is the entire image of this urine sample, and we develop a program to automatically locate the position of that calcium oxalate crystal. And also we compare our program with the manual counting, and they agree well with each other. So the take-home message here is that we can use this very simple platform to perform urine analysis. That typically is difficult to do. using the conventional light microscope, you need to have a clinician to look at the sample to screen like which type of crystal. Another implementation here is I'm working with my colleagues try to like send this device into the International Space Station. So this is how we try to miniaturize the device by using this voice coil actuator. So this is the very compact and portable device for this application. We need to minimize the size. Also, we need to minimize the weight of this entire device. So this is the operation on this portable device. So we have the laser diode. So we will illuminate the laser beam, and with this mirror, we can illuminate the laser beam onto this coated sensor. And we use this voice coil actuator to move this coated sensor to different positions. And we put the sample on top of the sensor, and we illuminate the sample, and we capture the data. Based on the measurement, we can recover the high resolution image of the object. Okay, so by using this portable device, we can capture, this is the raw image we capture. My question to our online audience is that, what is this object? You can think about like, what is this object? It turns out that this is the recover intensity. This is raw measurement. This is the recover intensity, and this is the recover phase. This is the snow crystal. So this is the raw image, recover intensity, and recover phase, and unmapped phase. And we can also plot the high map of this snow crystal. So another implementation here is the work we published in the photonic research, and this was done by my previous student Yang Liming. So we can perform label-free imaging with intrinsic polarimetric contrast. So the idea is pretty simple. So we are going to attach polarizer, ultra-thin polarizer on top of the coated surface. And then we can rotate the entire coated sensor to 4 different orientation to acquire the data and to perform the reconstruction. So this is the platform. So we can both translate and rotate this integrated polarization sensor. So with 4 different orientation, we can capture 4 different sets of diffraction pattern. And from there, we can recover 4 images. And with some Jones calculus, we can recover the orientation, retardance, and the birefringence map of this label-free biological sample. We also test this for like the whole slide potato sample. So this is the raw image, and this is the recovered gigapixel birefringence map. So this is the raw image we capture. This is the recover amplitude. This is recover orientation, retardance, and the birefringence map. We also test this for some clinical application. So here, this is the sample of a malaria-infected bus meal. So this is the raw image we capture, and then we can recover the birefringence map of this bus meal sample, and we can overlay the birefringence map with the face image, and you can see those malaria parasites within the bus cells. Lastly, we also test this on the unstained fibrous meal sample, so raw image, recover intensity, and this is the recover birefringence map. And you see those purple color, they locate at the position of these follicular cells. This is the DAPI autofluorescence image. So the take-home message is that we can use this birefringence map as a contrast to locate those cells within this unstained sample. We can also combine this coated ptychography concept with flow cytometer to create this optofluidic ptychography on a chip. And the idea is very simple. So we have a coated surface, and then we are going to translate the sample within this microfluidic channel. So this is the raw image we capture, and this is the recover intensity and the phase image of the different object. So this is the image sensor. This is the microfluidic channel with a coated surface underneath the channel. So this is the laser to illuminate the microfluidic channel. So this is the capture the raw image of the different types of object. So this is the yeast cell. So this is another type of cell. And then we can also compare our reconstruction with the conventional microscope objective lens. So this is another type of elongated object. It's a C. elegans. So we can recover the intensity and the phase image of this object. We can also compare with it with the image captured by the conventional microscope platform. So with that, I want to briefly talk about some extensions of this coated ptychography technology. The first one is we can consider the temporal correlation. So the idea is that in many time-lapse experiment, the object looks very similar at different time points. At adjacent time points, the object will be similar at adjacent time points. So by using this correlation property, we can reduce the image we need to do the reconstruction, and we can shorten the acquisition time and to perform real-time imaging. So this is the video to show you on the left. So this is the reconstruction by using this temporal correlation. On the right, without using the temporal correlation. And you can see that by using the temporal correlation constraint, we can see the real-time growth or real-time change of these bacterial microcolonies. And it's difficult to see these changes by using the conventional lens-based microscope platform. So we can also calculate how much it changes, for 30 seconds, 1 minute, 1.5 minute. So this is the device we image the bacteria. So you can see this agar plate, and we have the coated sensor under this Petri dish. So we have a huge field of view. It's about 1.2 centimeter by 1 centimeter. And if you zoom into different parts of the recover image, you can see the different bacterial colonies. We also use the device to monitor the bacterial culture from single cell to the microcolonies. And you can see here, for example, for this recover phase image, we can see a 3-layer structure from this microcolony. And for this one, we can see this 2-layer structure from the colony. And again, we have a very large field of view so that we can screen different colonies at different location, and we can plot their growth over time. So this is the dry mass. So this is a different types, different colony index, and this is the time. With this capability, we can use this platform to perform antibiotic drug screening to determine which drug is most effective to the bacteria. So here we try to add the drugs with different concentration, and then we try to monitor the growth of these microcolonies. And you can see that without any drug, you can see that the growth is exponential growth. And after we add different drug. After we add this gentamicin drug with different concentration, we can inhibit the growth of these bacteria. And from there, we can determine the minimum inhibition concentration of these antibiotic drugs. And this is important in the clinical setting to give the patient the right antibiotic drug. In this process, we also see some interesting behaviors of the bacteria. So, for example, if we add the antibiotic drugs to the culture medium, you can see that the cells doesn't divide anymore. It becomes longer and longer. So we can check the length of the bacterial cells over time. And certainly, we can also do this for cell culture. So this is the regular cell culture, the raw image, and we cover the phase image of the cell culture. And we can also perform the real-time imaging of this snow crystal. So you can see different types of snow crystals. The phase is changing. It's melting. Basically, the crystal is melting, and we can capture the entire process with this lensless device. So another extension here is that we try to perform this depth multiplex imaging. So in the conventional microscope platform, if you try to image the sample, you need to put the sample at different spatial location. And here we try to put the sample at the same location, but at different depth. So basically you can stack many biological samples together. And then we are going to illuminate the sample by changing the illumination angle. And we put the coated sensor at the bottom to capture the diffraction data. So this is our prototype device. So we have this car mirror. We modify this car mirror to change the illumination angle. So we can image like different stacked sample. Like this is multiple channels stacked together. So this is multiple slides stacked together. So this is the car mirror we bought. It's $25. So we can take out this car mirror. We just replace the mirror with a wafer so that we can change the illumination angle. So this is how we modify the car mirror. So this is the mirror to steer the instant beam on the sample. So this is the video to show you the operations of this device. We can steer this mirror so that we can change the illumination angle. And from the measurement we capture, we can then recover the multiple layers on top of this coated surface. So here we have 3 different layers. And here we have 5 different layers on top of the surface. And for each layer, we have a large field of view. So this is the recover phase and recover intensity image. We can also compare with the Guoan Zheng image. So lastly, we can also extend this for other imaging modalities. So one extension here is we can use this approach for conventional Fourier ptychography. So in the conventional Fourier ptychographic microscopy, typically we illuminate the sample from different instant angle, and then we try to recover the phase information. One problem here is that if you have a phase object with half 0, half pi, so this is the captured image, and this is the recover phase. You can see that the recover phase is wrong. It's not correct. And the reason is that by using this platform, you are missing those low frequency phase components. So if you do a Fourier transform performer analysis, you can see that you can only capture the high frequency component, and you are losing all of those low frequency components. And that's why the recover phase is not quantitative. So the solution is pretty simple. We are going to add a coated surface on top of the sensor and do this again. And this is the capture the raw image. And now we can recover the correct phase information. And if you do a Fourier transform to perform an analysis, you can see that we can get a perfect uniform transfer function by using this, I call this spatially coated Fourier ptychography. So we also run some simulation. So this is the Guoan Zheng. This is the conventional Fourier ptychography, and this is the spatially coated Fourier ptychography. You can get the correct phase by adding this coated surface. So this is the phase image of the conventional Fourier ptychography. So you can see that you are missing those low frequency components. And by using this, by adding this coated surface, we can get a perfect reconstruction compared to the Guoan Zheng. So this is just compare this coated Fourier ptychography with the conventional ptychography. You can see the difference there, and you can recover the correct phase by adding this coated surface on the image sensor. So this is again the biological sample. This is the conventional Fourier ptychography, and this is the spatially coated Fourier ptychography by adding the coated surface. Another extension here is we can perform a synthetic aperture imaging. So this is again the conventional ptychography setup. So we translate the object, we capture the image with the image sensor, and the resolution is limited by this spanning angle of the image sensor. So here we can translate a coated sensor. Instead of translating the object, we are going to fix the object. We illuminate the entire object all at once, And then we can translate this coated sensor to different positions to capture the data. And then we can synthesize a much larger apertures compared to this conventional approach, so that we can have a resolution improvement. So this is the setup, transmission mode, and the reflection mode. So this is the captured. This is the raw image by performing 3x3 scanning, so that we can synthesize. We can synthesize these 5.5 millimeter apertures, and by doing more scanning, we can synthesize a much larger aperture, and we can get much higher resolution. And similarly, this is the silicon wafer. So by doing 3x3 scanning, we synthesize a 5.5 millimeter aperture, and with more scanning, we can get a larger aperture and with a much higher resolution. So this is the we cover intensity and phase image, and this is the high map of this silicon wafer. Lastly, recently we also extend this approach for endoscope application. So if you remember this approach, we translate this coated sensor to different position, and now you can replace this coated sensor with fiber bundle. So we can translate this fiber bundle to different position. You capture the diffraction data, and then you can recover an image with a higher resolution. And actually, the concept is similar to synthetic aperture radar. So say you have an antenna. So this is the size of your antenna, and you try to image the object on the sea. And the resolution will be limited by the size of your antenna aperture. And the good thing here is that the aircraft, they have a flight path, so that you can acquire multiple images during the translation process. So you can capture multiple images there, and then you can synthesize a much larger virtual apertures by combining all the images you capture, and then you can improve the resolution. And actually, that is the concept of event horizon telescope. So this is the recover image of the black hole at the center of the Milky Way galaxy. If you use the conventional telescope to image it, you have a very poor resolution because like this antenna aperture, you have a very small aperture in this case, and the resolution is very low in this case. And the event horizon telescope, basically they translate this aperture by the motion of the Earth, by the rotation of the Earth, so that you can synthesize a much larger aperture there, so that you can get the more details of the black hole at the center of our Milky Way galaxy. The same principle applied here. So we translate the fiber bundle tip to different position. We capture the data, and then we can combine. We can synthesize a much larger aperture to get an image with much higher resolution. So this is the image model. So we have the object, and we have the fiber bundle tip. So we try to synthesize a larger aperture by moving this fiber bundle tip to different position, and then we capture the diffraction data at the end. So this is the object. The object will propagate to this plane of this coated surface, which is the fiber bundle tip, and then we will modulate this object or this light wave with the fiber bundle tip. So after we multiply the profile with the fiber bundle tip, we get this image, and then we capture the diffraction measurement with the image sensor. So I have a video to show you the acquisition process of this endoscope tip. So by hand holding this endoscope tip, you can acquire this raw image. By hand holding the fiber bundle tip, actually you are kind of like introduce some random motion to the fiber bundle. So that's why you can capture this. You can move the fiber bundle tip. So this is the recover modulation profile of this fiber bundle tip. You can see that they are changing over time a little bit, and we can recover this both the object and this modulation profile. And we perform this spatial temporal decomposition of this modulation profile of the fiber bundle tips. So we can like get 5 different modes, and this is the evolution index of the of this different profile. So this is the operation, the image. So this is the raw data we capture. So this is the resolution target. This one is the bus smear. You don't see any details of the sample. And then with all the data we capture, we can perform the high resolution reconstruction. So this is the recover image of the resolution target, and this is the recover image of the bus smear sample. So this is another demo. So this is the resolution target, the microcircuit, and this is a mouse column, and this is the recover image of these different samples. So this one is try to push the resolution limit. So by using this fiber bundle with 3.3 micron core-to-core distance, we can recover like the 500 nanometer line width on the resolution target. And we also test this with another fiber bundle. So this is a 200 micron diameter fiber bundle, and we can recover like 600 nanometer line width from the reconstructed image. We can also implement this with the distal chip endoscope. Like we try to remove the lens of this distal chip endoscope and replace the lens with this coated surface, and then we can perform again this ptychography imaging. Another advantage here is after we recover the light wave, we can propagate this back to any positions you want. So, for example, we can propagate this tilted bus smear. The object is a tilted bus smear, and then we can propagate the light wave back to different positions, and you can see that at different axial positions, different parts of the sample will be in focus. We can also demo this with another reflective sample. This is the corn sample, and we can generate this all in focus image, and then we can even recover the 3D map of this sample. And lastly, we can perform resolution improvement. So this is the original fiber bundle aperture, and by moving this fiber bundle to different position, we can synthesize a much larger aperture than the original fiber bundle. So with that, I want to conclude my talk. So by using this coated ptychography technology, we can get high resolution and large field of view. We can get a long working distance, centimeter scale working distance. We can perform refocusing after the data has been acquired. We can get nanometer sensitivity of the 3D shape. We can compete with the conventional interferometry system. We can perform neighbor field imaging with intrinsic polarimetric contrast. We can get like a real-time imaging to try to image the melting of the snow crystal. You can get depth multiplex imaging of a stack of the samples. We can also extend this approach for Fourier ptychographic microscopy with a uniform phase transfer function. We can also implement this approach for endoscope imaging to improve the resolution and to synthesize a much larger aperture. Before I end my talk, I also want to introduce a new journal called Advanced Imaging. It's also managed or operated by Chinese Laser Press. So we know this photonic research is the high impact journal managed by Chinese Laser Press. So recently, the same office, they launched a new journal called Advanced Imaging. So this is an open access, and this is also a highly selective journal covering all aspects in the field of imaging. And this new journal has an international editorial board with distinguished experts. So you can see some of the associate editors from these slides. So this is the topic, the scope of the journal. So if you want to submit, so if you have good work, you can consider this new journal as the venue of your next submission. So with that, I want to end my talk with a video created by my student Ruihai Wang. So he assembled this coated ptychography device from scratch. So I guess I need to be over time, but thank you, and I will be happy to answer the questions.
Thank you, Professor Zheng. Thank you for this great talk. I'm truly amazed by your curiosity, creativity. To be honest, I feel like you can turn anything you grab in your hand and use that for coded ptychography. And this is truly a powerful technology, right? You can turn a complicated 3D system into a lensless microscope. Thank you for the talk. So let's move on to question answer session. So first question for you is, in your presentation, you mentioned that the code were created using a layer of blood cell. Are there any materials or scattering particles that can be used to create this kind of surface? And what would be the advantages and disadvantages of using different materials?
Yeah, that's a great question. So in our prototype, we use the blood smear. So we use the blood cells on the image sensor as the coated surface. And it turns out that you can use any microparticles you want. And in the recent development, we try to make a thin film. So we have a PDMS flexible film. So we mix the microparticles with this thin film so that we can attach this thin film to any image sensor to convert it into a coated sensor. So basically, we are trying to make like a flexible metal surface you can give to like anyone you want, and then they can attach the film on top of their device. Yep.
Thank you. So second question is, you mentioned that this common face imaging method cannot properly recover the quantitative phase. Could you provide more details and an example to explain this limitation? And additionally, why is a coded ptychography technology capable of recovering the face with a uniform phase transfer function?
Well, that's also a great question. So the conventional phase imaging approach, such as the transport of intensity equation, differential DPC, differential phase contrast microscopy, and multi-wavelength phase retrieval or multi-height phase retrieval, or support-based phase retrieval, and Fourier ptychography. So all of this approach, they cannot detect the so for all of this approach, if you have a ping wave with a tilted angle, you have a ping wave, but you have a slightly tilted angle, right? In this case, the phase is a linear phase ramp. For all of those approach, those common phase approach, the image you capture is the constant. The image you capture only has the constant intensity value. So there's no way to recover that linear phase ramp. So that's the reason why most of these phase imaging approach, they are not quantitative. And why the coated ptychography can recover the correct phase, the reason is that we have the coated surface. So if you tilted the incident angle a little bit, the pattern is going to be projected. The projected pattern is going to have a positional shift. And that information can recover the correct phase ramp from the measurement. So that is the reason why we can recover the true quantitative phase with a uniform phase transfer function.
Thank you. And what is the resolution limits for the microscope you presented?
So the limit will be like NA equals to 1, so that will be a theoretical limit. So we are getting about 0.8 numerical aperture, so that is approaching the theoretical limit. But certainly you can change the different incident angle to perform synthetic aperture to further improve the resolution. So that is also a future direction we try to work on. Okay. And can your approach also be applied to synthetic aperture imaging with light? And if so, what will be potential applications and benefits of such an extension? Yeah, so in fact, that is very interesting question. So you know, for the Event Horizon Telescope or for other synthetic aperture radar, so they need to acquire the phase information in their measurement, and then they try to synthesize the aperture. And for our approach, synthetic aperture ptychography approach, we do not need to capture the phase information. You just translate that coded sensor to different position. So potentially we can use this approach to perform like some remote sensing application, try to improve the resolution of photographic lens, try to image a remote object with a higher resolution.
Yeah. Okay. Thank you. And also, can there's a Fourier ptychography microscope break the diffraction limit of optic system? And how do you view this issue?
Fourier ptychographic microscope,
yeah.
right?
Yeah.
Depending on how you, no. The short answer is no. So the best resolution of the Fourier ptychographic microscopy is NA equals to 2. So by changing the illumination angle, you can get up to NA equals to 2 numerical aperture of 2. So that is the best you can do with Fourier ptychographic microscopy. So unfortunately, it's no.
Okay. So last question. So when Fourier ptychographic imaging technique also applied to kilometer scale long distance imaging, how can one overcome the issue of excessive diffraction angles, which might result in a broad range of light field on receiving surface?
I'm not quite understand the question. So can you repeat that again?
So basically, this audience, he asked a different application. What you present, right, is more like a small scale object. So he's wondering about the Fourier ptychographic imaging technique. If that was applied to kilometer scale long range imaging, there might be some diffraction excessive issue of excessive diffraction angles. How do you overcome that?
Excessive diffraction angle.
I guess he might means the larger scale, maybe you shouldn't use diffraction angle, right? Maybe he means light from a broad range of angle.
I guess if you want to do this remote sensing types of application, you will still translate your photographic lens, right? So I guess my short answer is that by translating the photographic lens, you still can get a larger aperture than the single lens. So you can still break that limit. But I'm not sure if I fully understand the question. But if the person, you can also email me later so that we can discuss offline.
That's a good suggestion. I can clearly see a great mentor. See the last video prepared by these students. I think they're very lucky in your group. I guess you will have a lot of applications apply for your group this fall.
Thank you.
So as we are approaching the end of the event, honestly, I'm truly filled with gratitude with the impressive talk given by Professor Zheng. There are a lot of content. I'm truly overwhelmed by all the information presented by you. But it is really educational because you started with a very simple tutorial. You even explained to us how to pronounce the word, right? I want to thank you for agreeing to be the speaker for tonight. I also wanted to thank you for sharing insight in this coded ptychography that can be used for many applications, right? I guess it's beyond the microscope and endoscope, right? Basically, it's a way to use some random surface and encode information in those random surface so that it can decipher the original information carried by the incoming light.
Yes.
So, it's a different kind of smart eyes, right?
Allow you to see things surface.
Exactly. Thanks a lot. It's a wonderful tutorial for those of you who didn't catch the very beginning of the talk. I would encourage you to read the recorded video that we post online. And thanks for the presentation and for me, I think it's more than presentation itself. I clearly see a lot of excitement in research, curiosity, and commitment to innovation with high impact through the talk. So thanks a lot. And I also wanted to thank everyone who chose to sit with us tonight for the past hour. I wanted to give you my best wishes for your success in your future endeavor. and stay inspired and keep pushing the boundary of knowledge and the possibility to make the world a better place for our efforts. And also hope the insights we gain tonight can give you a glimpse of the amazing technologies enabled by scientific discovery and exciting interest in science. So stay tuned for the next spotlight and see you next time. And I want to thank Professor Zheng once again. Thanks a lot for being with us.
Yeah. Thank you.
See you next time.
See you. Bye.
Yeah. Bye.